This presentation is delivered by the Stanford Center for Professional Development.
Hey everyone, welcome. I have 3 handouts for you today. I put them up on the board because they're not in sequence. I went back and used the number for assignment 5 that I gave out a week ago today. So people who are watching on TV, make sure you go back and get the solution to handout 19. I think that's what it is. Let me just check. It is indeed. And so there's like all of these handouts in the last week that have corresponding solution sets. So make sure you actually download the solutions as well so you can compare your answers to mine and make sure that they're in sync with one another. You know you have the midterm on Wednesday evening at 7 o'clock to 10 o'clock in Hewlett 200, the huge room over there. Plenty of space, a lot of available room, so it'll be a great place to hang out for 3 hours. And I want to be clear that I am certainly covering code generation. You've seen that on the sample exams that I gave out last week. I am not going to include code generation for C++ features. No true references and no object orientation, no methods. So pointers, that's fine. Anything related to asterisks is real. That's real C, and I've emphasized that in the early part of the code generation. But references and methods, the code generation for that, it's not testable in the midterm. You will certainly see it on the final. I always know exactly what type of question I put on the final for that stuff, but you will not see it this Wednesday. Okay? I also promise to not have any preprocessor or linker or compiler stuff. I went through that kind of as a transition from C, figuring out how to build executables out of the C language. But I'm not going to test that material because I have tested it in the past and it just never goes well because it's so esoteric and we don't have any kind of real problems to exercise the material, so people just didn't do well, so I just stopped testing it. When I left you last time, I had written this farcically simple program that was supposed to model the selling of 150 airline tickets on a single flight. And so let me repeat that and point out why it's problematic and how we're going to move away from it. I went ahead and did something like this. I wrote it a little bit differently last time, but I'll write it like this. Num tickets is equal to 150. And all I want to do is I want to, in this brute force for loop, I'll write agent is equal to 1 agent less than or equal to num agents. Agent plus plus. I went ahead and I called this function called sell tickets. And I'm going to frame it in terms of the agent ID, the num tickets, div num agents, so that it's parameterized in terms of these 2 values right here, and ostensibly each ticket agent knows that he or she has to sell that many tickets as part of his or her function call, and then that's it. Just return 0 to satisfy the compiler. Okay, we're not going to allow anything to go wrong in this simple program. The implementation of sell tickets, it's not going to be rocket science. I'm going to write it a little bit differently than I would traditionally write it because I'm paying forward to the way we're going to change the example to in a second. Void sell tickets int agent ID int num ticks to sell. And even though it's a little weird, let me not use a for loop. Let me use a while loop. While it is the case that num tickets to sell is greater than 0, go ahead and do printf agent %d sells a ticket. Whoops. agent number, and then does a num tickets to sell minus minus. Finally, my arm is tired, but I'm going to keep on writing. Printf agent %d, all done. Agent num. This arm's going to be bigger than the other one by the end of the lecture. Okay, there we go. From a code standpoint, it's moronically simple. I'm not trying to revisit for loops and while loops. What I'm more interested in doing is figuring out why this, as a program, as a simulation, is really not all that good, in the sense that it's not really modeling what would truly happen. The way this is set up, and I'm speaking like as if this is new material, but it's not. It's clearly going to be sequential, and ticket agent 1 is going to sell all of his or her 15 tickets before anything happens with ticket agent 2. So you know that the printout of this would have 160 lines, 16 lines per ticket agent. Okay, I'm sorry, 16 lines per ticket agent. But they would be sorted all ticket agent number 1, followed by an all done comment. That's the 16th. Okay, does that make sense to people? Okay. And there I'm sorry, 165, because there's 15 agents going on here. I'm sorry, no, there's 10 agents, so 160. I'm just confused. But everything's going to be all about agent number 1 before it's agent number 2, before it's agent number 3, etc. I really don't like that. Okay. This is a fairly compelling example where if we're really trying to model the simulation of an actual airline ticketing room, that you want to see all of these ticket agents running simultaneously and working, not competing, but working collaboratively to sell all 150 tickets at the same time. I'm going to simplify the problem a little bit and let all of them just work to sell 15 tickets, knowing that because of the way the code is written, that if everybody sells their 15 tickets, all 150 tickets will be sold. But this will do it sequentially. I don't want to do it sequentially. What I want to do is I want to set it up so that all of these ticket agents follow the same function, follow the same recipe for selling tickets, but they all seemingly run at the same time. Okay? Now, in order to do that, we have to use a thread package, a package or a library that we've written here at CS107 land in order to do that. It turns out that while C and C++ are standard, thread packages and libraries to help support the type of thing I want to do here are not standard across platforms, and to the extent that they're standardized in Unix and Linux flavors, it's actually very difficult to use. It's like quirky syntax. It's like worse than like C++ iterators in terms of syntax. So we actually packaged and layered some stuff on top of the thread libraries that are available for Unix and Linux, and wrote a slightly easier thing to deal with. I'm just going to write the functions to show you how this stuff works, and you can kind of intuit meaning as to what these functions are supposed to be doing for us. Now, when I talk about a thread, I mentioned this briefly on Friday, thread is really short for single thread of execution. So when I'm talking about a thread, I'm talking about some function that's running, presumably in the company of other threads at the same time. I want to set this up so that each of the 15 ticket agents operate like dogs at a racetrack, and that I really want to lift the gate. And it's not so much a race with each other as it is just a race to the finish line. But all 15 of these dogs, all 15 of these threads, are going to be interesting in following whatever recipe it takes to complete the function. And when all of them finish, you know that all of the work has been accomplished. Okay? So what I'm going to do is I'm going to leave this function as is. This isn't going to change, at least not for the short term. And I'm going to go with a different for loop here. A slightly longer code block here. After I frame the simulation in terms of the number of tickets and number of ticket agents, I'm going to call this function the init thread package. I'm going to pass in a false. I'll explain what that is in a second. You know how in CS106 and 106V and 106X you called init graphics to bring up the graphics window, or you called init boggle graphics, or whatever you had this one static routine you call up front to kind of set everything up? If you want to use the thread library on our system, you actually have to tell the executable that you're going to be doing that. This is just an initialization routine that has to always be in place before you call any other function in this library I'm teaching you right here. Okay? This basically says that I'm going to be using threads. This false means please don't print any debugging information. If you pass a true in there, you get all types of information about how the threads are executing. Now what I'm going to do is I'm going to repeat the for loop. Int agent less than or equal to non-agents agent plus plus. Here is how you set up the actual, this is how you set up the dogs at the racetrack. What I want to do is I want to create a name that's unique to a particular ticket agent. I'm going to do that by declaring this in-place buffer. If you haven't seen this function, it's not the emphasis, but I also will show it to you. This is in the handout. I'm going to printf, not to the console, but to a character buffer. There's a function called sprintf to do that. Rather than actually echoing the characters to the screen, I echo the characters in place to a character array and make sure it turns out to be a C string. The character buffer that functions as that console of sorts begins at the name address. Okay? And as long as I don't print more than 32 characters, I won't overrun the boundaries of this thing. This is the structure of what gets printed. And then I will fill in agent. So for all intents and purposes, on the 0th iteration, or the first iteration of this thing, after that sprintf call is made, name contains, goes from garbage to the C string, agent1 thread. The reason I do that is because I want to call this function called thread new. And the name actually serves as the name of the thread, and it's also helpful for debugging purposes should you be passing a true to that init thread package function. And then you go ahead and you pass in the address of the function that you'd like to execute in a single thread of execution. Okay? This right here, it's just an arbitrary function pointer. All of the arguments have to be 4-byte arguments. That's just a constraint of the system. So you can pass in ints and floats and pointers, but you can't throw in structs or characters or shorts. It'll confuse the system. You have to tell it how many arguments are expected of this particular function. We're going to have scenarios where the thread functions don't need to take any arguments. We're going to have a scenario like we do right here where sell tickets takes 2 of them. There's a ... involved in the prototype of thread new, which is why we have to actually pass in an explicit number. And then beyond the 2, you pass in the numbers that are of interest. So agent and then num tickets divided by num agents. Now this does not actually prompt sell tickets to start executing. All it does is it lines it up at a gate, and that's all that happens. Yep.
The name buffer, why do we send it that?
Well, the prototype of thread new just requires a thread name right here. Okay, so we have to do it just because the library said, but that's a lame answer. You really do want something available to you to identify the particular thread that, for instance, is failing you during the debugging process. And if you have 15 of these things, okay, does that make sense? Or I'm sorry, you have 10 of these things, and then one of them is failing, or one of them is never exiting, which is actually a common thing we'll see in multi-threading. You want to be able to know which of the threads is not exiting, so you can go and look at the particular implementation of that function. Okay. This sets all of the dogs and lines them up. This function, run all threads, lifts the gates. Okay. So procedurally, what happens up front is we say we're using we're using threads, and then you lay down gates 1 through 10, all of these things that are going to follow the sell tickets recipe. That's what they need to follow in order to run from the finish line, from the starting gate to the finish line. And then this basically sounds the bell, fires the gun. Okay. This as a function blocks until all of these threads actually finish and run to completion. And then when it detects that all, in this case, 10 threads have finished, this returns and it passes on to what will be the end of the entire function. Yep.
So, if I wanted to do the same process somewhere else, is this an init thread package and run all threads within the scope of the function?
It actually does not have to be in main. It's just most conveniently put there.
So what if I had another function that runs threads as well? When I call run all threads, does it just run everything out there?
What has to happen is that before you call run all threads, you have to call init thread package exactly once, and you have to set up all the threads, whether it's directly in main or through subfunctions, to set up all of the dogs. Okay? Does that make sense? This actually fires the gun and tells all the threads to start running. It turns out that as threads execute, as part of their implementation, they can themselves call thread new. Does that make sense? So threads, the main function is actually spawning 10 threads right here. The threads, they won't in this example, but the threads themselves can spawn their own child threads, okay, grandchildren threads, whatever you want to. The ridiculous metaphor I have is that somehow, like, while a dog's in the race, it gives birth to, like, 3 new babies and throws them back to the beginning of the gate, okay, and says, please run. And sometimes there are interesting concurrency issues that can come up with that type of thing, but I'll actually get to that with a more advanced example probably Wednesday or Friday, okay?
But for those other babies, you would call another run all threads?
No. This just basically says now we're in thread mode. Okay. Once this has been called, all threads that are ever created in the process, even if they're children threads, just start executing immediately. Okay. So as far as this is concerned, I want to do one thing. I want to just invent a function right here. If random chance 0.1, I want to call a thread sleep function. And I'll just pass in, let's say, 1,000. Okay. That thread sleep basically says, as part of execution, if a thread is running and it executes the thread sleep function, that it pulls itself off the processor for at least, in this case, a second. That number that's passed as an argument is expressed in milliseconds. So this means that every time it flips a biased coin and it comes up heads with probability 10%, or 0.1 rather, it'll force it to halt. Now that isn't the only way a thread will halt, but this is a way for you to programmatically tell a thread to stop running. But let's forget about thread sleep. I shouldn't have talked about that yet. What actually happens is that when you spawn off 2 or more threads, or even technically one child thread, but 2 or more is when it's interesting, run all threads establishes something of this heartbeat. Okay, and in between the tap of every single finger, some different function, usually in a round-robin status, but a round-robin fashion, but not necessarily, gets the time slice that exists in between the 2 finger taps. Does that make sense? So it's like agent 1, agent 2 runs, agent 3 runs, agent 4 runs, in that round-robin manner, okay? And however much progress they happen to make in that time slice is the progress they make. Now, if I don't introduce any randomization, it's probably the case that on a real system, it would execute the same exact number of assembly code instructions, okay, or very close to it. So everyone would make exactly the same amount of partial progress with each time slice, okay? Does that make sense? To make it a little bit more real world, we introduce some stochastic process here where things all of a sudden get a little bit random, and maybe it's the case that ticket agent 1 sells 2 tickets in his or her time slice, and then gets pulled off the processor instead of actually being allowed to sell 2 more tickets. Maybe ticket agent 2 comes next and sells 4 tickets. Maybe ticket agent 3 comes next and sells 4 tickets because this coin flip never comes up heads. Does that make sense to people? Yep.
So when we do thread sleep, which thread sleep?
Well, the one that's executing, the one that actually calls it. Okay, I mean, it's only called once, but the 10 dogs up there are actually each following this recipe. They each have their own little pointer into the assembly code that this compiled to. Okay? And if they happen to jump into this function right here, then the thread that actually is stuck inside that function is pulled off the processor, and it's even pulled off of what's called the ready queue and put on this thing called the blocked queue until this number of milliseconds in terms of time elapses. Does that make sense? Yep.
When we call thread new or run all threads, is there any control over how many clock cycles each one will get?
Not in our system. Some very sophisticated thread libraries, I don't want to say very sophisticated. A lot of thread libraries, they don't actually they don't always give you control over the amount of time that's in a time slice. They do want that to be somewhat regular because they don't want you to have unpredictable results, certainly not during the development process. Even though ours does not, some thread libraries, particularly the one in Java, this is the one that everybody will be the most familiar with by the end of the year if you're continuing in by the end of next year when you take 108, you learn about the thread library there. You can attach priorities. There's only 3 degrees of priorities I'm sorry, that's not true. There's 10 levels of priorities in Java where you can like assign a priority of 1 to 10. And then usually it's the case that they're all sorted and all the threads with priority 10 execute and run to completion before anything with priority 9 is given time. Okay? But we don't have any of that here. We really just want to think of all threads as equally likely to get the processor for a particular time slice in this round-robin manner, unless there are other things in place that actually block it from being able to make progress. Okay? So think about this line as basically either really not blocking it at all or blocking it for an arbitrary amount of time. Okay? What I want you to imagine here is what type of printout you might actually get in response to this thread implementation. You might get 3 printfs, agent 1 sold, whatever I wrote, sells a ticket. May happen like that. Maybe it sells 3, maybe agent 2 comes next. Maybe agent 3 sells 5 because that's how much time slice allows. Maybe 5 is actually the most you'd actually see up front as the number of tickets that's sold. But you understand what I'm getting at here. Okay? Does that make sense? It would just keep on cycling through all of them. Maybe it is the case after 130 or so lines that for whatever reason agent 7 all done gets printed. Is there an exclamation point? Yes. And then maybe it's the case that agent 8 sells a ticket. Agent 8 all done. And then eventually maybe it's the case that for whatever reason agent 4 is the last one to sell a ticket. And this is just representative of the type of output you might see from this. Now, there's nothing interesting about this from a simulation standpoint because there's really no compelling reason from a performance standpoint to use threading here, except that you're trying to emulate the real world a little bit more. Okay, there are situations where you want to go with threading for performance reasons. This isn't one of them. I'm just trying to illustrate the thread package. Yep?
So if you didn't do the thread sleep, would you see agent 1 sells a ticket, agent 1 sells a ticket, agent 1 sells a ticket? Or is it agent 1 sells a ticket, agent 2 sells a ticket?
You would actually see the thread library has no notion of what a while loop is. So it's not like it detects that you've jumped back and uses that as a signal to pull it off the processor. Let's say that the typical time slice is 100 milliseconds. However many tickets can get sold in 100 milliseconds is how many would be published. Sometimes it's going to be partial. Maybe you're going to be halfway through the implementation of a call to printf, right, when it gets pulled off the processor. Okay? And then when it gets the processor back, it continues with through the partial execution of printf to complete it, return, and decrement the num tickets to sale count. Okay? Does that make sense?
There's no way to split up the 100 milliseconds? Like, let's say you have 2 processes that you want to run like parallel, but you want them to switch back and forth faster than 100 milliseconds?
You can't. Well, in our thread package, you certainly do not have that. I have to think that there are some thread packages out there that do allow you to control the time slice. It's usually not that high priority. Usually you don't introduce threading into a program to have control over the time slicing. You really just do it to have concurrency in the first place. Let the thread manager figure out which threads can make the most progress. In an ideal world, we actually don't want to pull agent 1 off the processor at all if agents 2 through 10 are in extremely long phone conversations. And that doesn't happen here, but in a real simulation, you might want agent 1 to keep on selling tickets if all 9 of the threads are blocked on something else. Okay? This is just in place to illustrate the thread new and the run all threads in the init thread package concept. Okay? Yep?
2 questions. So thread sleep it just sort of pulls that one off the queue.
That is correct. Yeah, you have to think that this is actually being called by 10 different threads in this setup. It's only written once. Okay? And it's basically like 10 copies of the same book. But it's not even that. It's actually 10 copies of the same web page, and the web page itself is hosted on one machine. Okay? Does that make sense? There's one copy of the code. 10 independent threads are following the same recipe.
Correct.
Okay?
And is there any disadvantage to calling run all threads directly after initiate thread package?
Well, it has to be called, oh, you mean, I see what you're saying. In other words, to set this up and maybe call it right there with the idea that these actually run immediately. I know what you're doing. In our system, it wouldn't work because this is a function blocks until all threads have completed. So what would happen is you would call a init thread package, you would call run all threads, there wouldn't be any. So it would return, and then it would go on and spawn these threads that aren't allowed to run because run all threads is actually returned. Okay? So this is just idiomatic. Do this, set up at least one thread to run to make sure that all of the work that needs to get done gets done, but in this concurrent manner as opposed to the sequential manner, and then call that just to fire the gun. Okay? Yep.
Cell tickets outside the whole thread context and encounters that thread sleep command.
That if you, in other words, it's not inside a thread. It could work. The way that the thread library works, the main thread is also a thread. So if, as part of a sequential execution, it's really not sequential. It happens to still be in a thread. It just happens to be the main thread as opposed to one of these child threads that spawned off by what was reachable from main. Okay. Now, I have to say I've never tested that because I've never given an assignment or done an example where I exercise the edges of the thread library. I've just kind of gone with the way it was designed to be just so I can make progress. But you could try it out when the assignment goes out and see what happens. But you'll never see a meaningful example from me that actually relies on that. Yep.
You said a thread doesn't know if it's in a while loop. Does it know if it's in an instruction? Like, does it know that, say it loaded num gets to cell, decremented it, and then the timer went off? Does it know
Right. That's certainly the most interesting part of today's lecture, is that right now, you know enough about code generation, I'm hoping, because you're going to be tested on it in 2 days, that this right here is, what we say is that it's not an atomic operation. It looks like it's atomic because it's written on one statement right here. But what happens is that this really corresponds to probably what would be, it's a local variable, it would be 3 assembly code statements, this line right here. Does that make sense to people? So it's going to basically load num tickets to cell into a register, decrement it by 1, and flush it back out. That's what, in the normal context, this would compile to, right? There's no requirement. In fact, the thread library has no clue when it's executing one assembly code instruction, whether it's on the boundary between 2 C statements or whether it's midstream between something that was generated from 1 C statement. Does that make sense? So C instructions are not atomic. Okay, and this is going to be a complexity we're going to start to solve in the last 20 minutes of lecture right here. So when it gets swapped off the processor, it could be right before the first instruction of the 3 that this compiles to. It could actually finish right after the third of the 3, or it could be pulled off the processor 33% or 66.7% of the way through the code block that this compiles to. Does that make sense? So basically the takeaway point, and this kind of foreshadows what's going to happen in the next few minutes, is that it can make partial progress on the minus minus. It's almost like I minus minus it, and it stops. And it's pulled off the processor. And it's going to pick up from there when it gets the processor again. Does that make sense? But something else in the next few time slices is going to make some more work. Okay? Or do some more work. Yep?
Can we stop midway through an atomic function?
No, every single assembly code instruction is either not executed or it's executed in full. Okay? I mean, that's just because everything is quantized on the clock cycle. Okay? The thread library and the switching between threads, that's managed by this very high priority thread that always gets the processor back every time slice, at the end of every time slice. And it itself is effectively written in assembly code as well, because that's what it compiles to. Okay? Yep?
I was wondering how much time this will take. So if I were to not do this, not concurrently, just all of Agent 1, all of Agent 2, it would take the same and probably less than.
Yeah, that is absolutely true. Like I said, I would say there's not a compelling reason from a performance standpoint. I'm just trying to come up with a very simple example to illustrate just the concurrent idea. For assignment 6, I mentioned this before, but you were going to adapt your assignment 4 solution, or mine for that matter, if you want, to use threading. Now you know how painfully slow the loading process is, where you just watch this article, and this article, and this article. Most of the time is not spent actually pulling the text. Most of the time is spent waiting for a connection to some server in Boston or in London to actually be established. And once that's in place, pulling the text over is actually fairly fast compared to that. Does that make sense? Yes, no? Okay. So the reason it takes so long is because you have 500 articles to index, and you do one at a time, and you feel every single stall time in sequence. If you use threading, and this is the best example of all of the ones I'm going to have, I think, where threading is really important. If you use threading and you spawn off 12 download from BBC server threads, okay, all of them make enough progress, all of them try to open the connection, and because that's considered a block at the kernel level, it's pulled off the processor. It's this much more harsh version of thread sleep. Okay, but it sleeps for a meaningful reason because it really can't make any progress, and the thread realizes that, and the thread manager realizes that, so it pulls it off the processor while it's waiting for the connection to be established. Does that make sense? Well, imagine that all happening with 12 threads. All of those dead times that are associated with the network connection, establishing the network connection, they all align and overlap and pipeline in this way that really saves us a lot of time. Does that make sense? So if you have if, let's say, 80% of the time, it's probably more than that, 80% of the time for any one thread is associated with establishing that network connection, and you overlap all of those times, think about the amount of speed up you're going to get. You're going to be so delighted with the final product of assignment 6. I mean, I'm not just saying that because I wrote the assignment and I want that to be true. It really is, in fact, the case, because once you get it working, what used to take 7 or 8 minutes to load, 10 minutes if I add more things to the RSS feed, downloads in a matter of, depending on how savvy you are, between 15 and 45 seconds. Okay, and that's obviously what has to be in place in a real-world solution, because someplace like your typical RSS newsfeed reader, like Google, doesn't have the time to have one machine pulling every single article from the planet so that it can build Google News. It really does use a much more sophisticated version of what we're going to be doing here to index everything seemingly simultaneously. Okay, it happens to use a lot of computers at the same time to do it. Okay, does that make sense to people? Okay. Yep. Go ahead.
Last lecture you mentioned about downloading certain files. I was thinking, well, you only have so much download capacity. Like you only have so much speed you can download, or so much size of file to download a certain amount of time. Like how can you download more than that?
But the thing is, you're actually not. Like as far as the downloading is concerned, if you're dealing with a uniprocessor and you're dealing with one processor with one RAM and one core, then you're dealing primarily only with the ability to index one article at a time as the text comes through. So you're right, you don't save time for the actual pulling of the text and parsing of it and updating your hash sets, but you really save the time with the network connections, and that's what's the huge win is. Okay? Does that make sense? Okay. So what I want to do here is I want to complicate this problem a little bit, but complicate it in a meaningful way. In a real-world simulation, it might be the case that you have 2 ticket agents, and you have to sell 10 more tickets, and somebody's stuck on the phone because they can't decide whether they want to buy the ticket or not. And so the other ticket agent should be able to sell 9 or all 10 tickets, while the other one is blocked with some time-consuming customer. Okay? So what I'd rather do is I'll rewrite this in a second, but I want to change the prototype. What I'd rather do, rather than actually instructing each particular thread to sell a predetermined number of tickets, I'd rather grant them all access to the same shared integer, the master variable that stores the number of remaining tickets, and do something like this. Int agent, then int star num tickets, and I'll put a P there. And I'm going to leave the prototype. Actually, I'll close it off for the moment. I'll change this up here in a second. Okay. What I want to do is I want each agent to know what their badge number is, but I also want them to be able to go back to the main function and find the master copy of the number of variables that are remaining. I'll change that up there in a second. Okay. This is basically the equivalent of the one master copy of your checking account balance. That's supposed to be that every single ATM machine in the world is supposed to have like atomic transactional access to. Does that make sense to people? Okay. So in a nutshell, I'm not going to bother with the printfs because they're not as interesting to me anymore. While it's the case that num tickets P is greater than 0, okay, go ahead and do this. I don't know what word that is. Num tickets P, I need the parentheses here. And then you can imagine the printfs interspersed where they would be interesting to us, but I'm obviously interested in selling a ticket and deducting the global counter. The setup up here would change just slightly. So all I would do is I would pass in ampersand of num tickets, like that. And as opposed to each thread running its own function, where each thread has its own stack frame with its local copy of what was num tickets to sell, now all of them maintain a pointer to that what is now 150 at the beginning of execution. Does that make sense? So just to draw some pictures, here's the stack segment. Here is the main thread and its stack frame. All 10 other stack frames for the 10 other executing threads all have pointers to that 150 inside. And that's how they all kind of keep dibs on how many tickets there are remaining to sell. Okay? Does that make sense? Now the problem, and this is actually not even the full problem, but I'll simplify the problem, make it seem like it's easily solved, is that I, as ticket agent 1, might come through and I might commit to that test and say, oh wow, there is, in fact, 1 ticket left. That's greater than 0, so I'm going to commit to selling it. Make sense? And then, boo-hoo, it gets swapped off the processor right after the curly brace, but before anything associated with the num tickets minus minus. Okay? Make sense? And so it gets swapped with the processor, and thread number 2 comes in and executes the same test. Oh, look, there's 1 ticket left. I'm going to sell it. And it comes in and it commits to trying to sell it, but it gets swapped with the processor. Same thing for thread 3, thread 4. It could be this diabolical situation where everybody is really excited to sell the 1 remaining ticket. They're all eventually going to, they don't go back and recheck the test after they get the processor back. That's not what's programmatically encoded. So they're all going to try and decrement this shared global. And so 1 could potentially go down to -9. Okay, this is not why, I don't think this is why airlines overbook flights. Okay, but you can understand the type of concurrency problem that exists here. This is more interesting than the first version because all 10 of my threads are actually sharing a resource. Okay, they're all depending on the same shared piece of data, and if they're not careful in the way they manage the shared data, and if it's part way through the execution and it makes decisions based on information that will become immediately stale if it's pulled off the processor, then the integrity of the global data can actually be mucked with and actually be compromised. So at the very least, we want this all the way through that to more or less be executed in full. Okay? So basically what the top bracket and what the bottom bracket does is it kind of marks what that thing right there is what's called a critical region. It's like once I enter this region, no one else is supposed to be in here while I'm doing surgery on that global variable. Okay? Does that make sense? Now there's nothing in the code that actually says, please, other threads, don't come in here because I am. Like, there have to be some directives that are put in place to block out other threads from going in here. Okay? This is kind of like the situation where you're really glad the bathroom door locks because if you're in there, you don't want, because somebody else decides that they're going to use the bathroom, for them to have the privilege of just walking in because they're running in their own little thread. Okay? You actually have to somehow have a directive in place, this thing called a lock. I'm going to frame it as a binary lock, I think for obvious reasons, because you only want one person in the bathroom or in the critical region, right here, okay, at any one moment. Okay? So what I want to do is I want to talk about the most common concurrency tool that's in place to actually help delineate what is considered to be a critical region. It involves me introducing another variable type. Actually, I'm trying to think if I want to do this. Is fine. I want to introduce something called a semaphore. And I'm going to call it lock. And I'm going to set it equal to semaphore new. Takes two arguments. The first one I don't care about. The first one is going to be some integer. Now, I'm just introducing semaphore like it's a word you're all familiar with. I know you probably know what semaphore means in a general sense, but in a programming sense, what a semaphore really functions as is a non-negative integer. At least in our library, it's considered to be a non-negative integer that, as a data type, has functionality that supports atomic plus plus and atomic minus minus. Okay? This basically sets this this glorified integer equal to 1. Okay? The minus minus and the plus plus against this lock comes in the form of two different functions. There's a function called semaphore weight, which in this case would be take the lock variable. And there's also another function called semaphore signal, which also takes a semaphore. Now those are functions that behind the scenes emulate minus minus and plus plus, but they just figure out using special hardware or special instructions in the assembly code language to actually take the integer that's wrapped around by the semaphore, in this case what's initially a 1, and provide atomic minus minus. Okay? So in other words, this right here would be decremented to 0 if this were called against it. This would promote it back up to 1. Okay? The reason that wait is the verb here is because we're going to generalize a little bit, and you think about the semaphore as tracking a resource. In this case, there's exactly one person allowed in the bathroom, or there's one person allowed into the critical region, okay, which is why that's the 1 in the first place. And you acquire that resource, or you wait for that resource to be available, and when you don't need it anymore, you signal it, or you somehow release the lock so that someone else can pass through if they were themselves waiting on it. Okay? Make sense? So what I want to do is I want to use one of these, I should make, there's one key point I forgot to make, is that because the semaphore integers in our world are never allowed to go from non-negative to negative, there's one special scenario that's handled by semaphore wait. If semaphore wait is passed to semaphore that at the moment it analyzes it is surrounding a 0, it doesn't decrement it to -1. It's not allowed to do that. That's just the definition of what a semaphore is. If it detects that it's a 0, it actually does what's called block. And it blocks on that semaphore. It actually pulls itself off the processor because it knows that it's obviously waiting, presumably, for some other thread to signal that thing before it could ever pass through that semaphore wait call. Does that make sense to people? Okay. Basically, if I'm jiggling the door for the bathroom, like we always do at restaurants to wonder whether somebody's really in there or not, okay, you need, before you can really pass in there, you need someone else to release the lock, some other thread or some other agent in the form of a semaphore signal call before you really can go and open that door. Okay, and then you can lock it yourself. Okay, does that make sense to people? Okay, so what I want to do here, actually I should probably clean this up a little bit. No, this is okay. What I want to do is I want to pass in 3 arguments to sell tickets. The reason I want to do that is because I want to tell the ticket agent what his or her ID is. I want to pass in the address of the shared resource, but I also want to pass in this thing I call lock. Now, the semaphore type is actually a pointer to an incomplete type, so it's always 4 bytes, so it's okay to just pass it verbatim. It's not copied, it actually shares some kind of struct behind the scenes that tracks the integer inside of it. And then the prototype of this would need to change to take a semaphore. I'll call lock. And this is the implementation I want to go with. While, I'm going to simplify it a little bit. I'm going to say while true, I'm going to semaphore wait for the lock. As a thread, I have no business following that pointer and looking at its value and comparing it, using it in any sense, even comparing it to 0, Because as I advance through the execution, I can't trust that that comparison actually is meaningful, okay, if at any point during progression it actually gets swapped off the processor and other threads can go and muck with that shared variable. Does that make sense to people? Okay. So what I want to do is I want to wait on the locked bathroom door. And if I happen to be the one that first detects that it's unlocked, and I can go in and in this atomic manner actually do a decrement. So as I detect that it's been promoted from 0 to 1, I actually take it from 1 down to 0 and actually pass through the semaphore wait call. Then I can do this. Num tickets P is greater than 0. Or I'm sorry, I'll change it. If num tickets P is double equal to 0, then I want to break. Otherwise, I want to do this. I want to put whatever printf I have right here to say that I sold a ticket. And then I want to semaphore signal the lock. The one thing I want to do here is that if as a thread I acquire the lock and I notice that there are no more tickets to be sold, when I break out, I don't want to forever hold the lock on the bathroom. Okay, this is the equivalent of like jumping out the window of the bathroom and leaving the door locked. But if you can programmatically unlock the door from afar, you're no longer in the critical region, but you still somehow managed to unlock the bathroom door. Okay. Now, there's a couple of points I can make about this just to let it rest for you, because this is probably where I'm going to leave things until Wednesday. I initialize the semaphore to 1 up there. That basically functions as a true, or in the case of a semaphore functioning as a binary lock, it basically says that the resource is available to exactly 1 thread, and the first thread to get here actually does manage to, in an atomic way, take the 1 and do a minus minus on it down to 0. Because it actually committed to the minus minus, it returns. It executes this. It takes the 0 back to a 1, 1. It may come back around and take the 1 back down to a 0. But it's always like lock, unlock, lock, unlock, lock. And maybe it actually gets swapped off the processor right here. That would normally be dangerous, except that it's leaving the semaphore in a state that it surrounds a 0. Okay? So that if some other threads get the processor, and they certainly will, then they come here and they basically are blocked by a 0 semaphore that they're waiting for. And you can't do a minus minus against a 0 behind the scenes. So they are immediately blocked on the thread that owns the semaphore, which was the first one I was describing. And it's only considered for processor time when the thread manager detects that somebody signals that semaphore, because that's the only hint it has that the blocked threads might be able to make progress. Does that make sense? Okay. So just because there's a semaphore wait call and a semaphore signal call, don't think that threads can't be, the thread that owns this lock can't be swapped off. Okay? It can be swapped off right here, and it can allow all the other threads to make as much progress as possible until they really are blocked. Okay? But once they're blocked, this thing would have to get the processor again. Okay? Does that make sense? Yes, no? Okay. Imagine the scenario where I accidentally, and this is actually the type of thing you have to be careful about because it's so easy to type a 0 versus a 1 when you're typing a lot of them. If I do that right there, this creates a situation that you have to really be worried about when you're dealing with concurrency and threads, is that if I accidentally lock the bathroom door before anyone comes to the party, everybody's going to be blocked, and no one's in a position to actually unlock it, at least not the way I've coded things up right here. Does that make sense? If I make the mistake of putting a 0 up there, then every single thread will get this far, and they're all going to be thinking that someone else is going to be signaling that semaphore, so they're all 10 of them are pulled off the processor, and everybody's just waiting. Okay? And that scenario, I don't want to say it's common, it's not supposed to ever exist, but if you have this type of bug in your code, you have what is called deadlock. Okay, where all the threads are seemingly blocked on some resource that they think someone else is going to be taking care of. But that isn't the case because of that one little bug I put up there. Okay? Make sense? If I have the opposite error, and I do that right there, from a programmatic standpoint, if it's going to be 2, it might as well be 10. Okay, if you're going to let 2 people in the bathroom, why not let all 10? If you're going to actually let 2 people go into the critical region and muck with global data at the same time, then you have the potential for kind of messing up, for having 2 threads deal with this shared global variable in a way that they really can't trust each other. Does that make sense to people? Okay. So there's that. So the real answer here is that this, in this particular case, should be a 1. Now, we will see situations where a 0 is the right value. Okay, we will see situations where 2 or 5 or 8 or 20 or 64 are the right values. But for this one scenario where I'm using a semaphore to basically limit access to what's clearly identified as a critical region, okay, that is the common pattern for using a semaphore. Okay, question right there?
Do we have 2 signal locks?
2 signal locks. Oh, this one right here. This is the one that I actually is there whenever I actually do a decrement. Because I can break out of the loop right here. If I break out of the loop, I circumvent this final call right here. But other threads may be blocked on the semaphore right here. All they need to do is to verify as well that there are no tickets left. Okay? But you still have to allow them to programmatically get there so that they, as threads, can also exit. Okay? Does that make sense? Okay. Yep.
Is there something stronger than a semaphore that actually won't let the thread get pulled if you have something time sensitive?
Actually, just priorities is really it. And then even then, it's probably up to the thread manager as to whether or not, what would probably happen is a really sophisticated thread manager might actually know behind the scenes, before it even grants the thread the processor, that there's only one thread with that priority. So it might actually have, and I don't know that this is the case, and I'm just like speaking in terms of implementation details. It might say, okay, well, that's the only one of that high priority. So unless we see it spawn a thread of equal priority or higher priority, we're just going to let it run until it actually blocks itself, in which case we don't have any choice. I don't know that many systems do that. I think the mild hit that they take by just taking a processor off and spending like 2% of the time that would otherwise be available, if they have to complicate the implementation of the thread manager just to get that win that doesn't come up all that often, they might not bother. Maybe they will. I just don't know. But it's technically possible to do it. Okay, so we have more examples come Wednesday, but I just wanted to make sure you all got this. Have a good night.